Okay. Good morning, people. Right. So I hope people are just joining. I see some numbers. Okay, we'll wait for maybe 2-3 more minutes. Let your friends join. Okay. So I think people should be ready by this time. I hope. Right. Fine. So I think we'll start. Right. So we have been saying the chapter solutions. Right. So if you can recollect what and all we saw, right? So first class we started with what do you mean by a solution, right? It comes under something called as mixtures, homogeneous mixture. Solution is a homogeneous mixture, and then we went on to see what are the different. Yes, some problem. Okay, fine. So we went on to see what are the different types of solution, binary solutions, tertiary solutions, so on and so forth. And then based on whether it's a liquid solution, solid solution, gaseous solution, all these things are possible. Then we went on to see saturated, supersaturated, and unsaturated. These are different types of solutions. Then we went on to see what is solubility, right? So what is the criteria for a substance to get dissolved in a particular solvent? We even gave a quote, like dissolves like, right? So there is one type of substance that will be dissolved only in that type of substance. Polar solute, polar solvent. Non-polar solute, non-polar solvent. So, and then we went on to see how this solubility is affected by the pressure. That's where we saw Henry's law, right? So then we went on to see, I think, what is vapor pressure, right? So vapor pressure we saw, what is that, right? And we went on to see if I mix two liquids, what is going to happen to the vapor pressure, right? We generally we say that vapor pressure will decrease, right? So we even have a formulas: PA is equal to PA naught XA, PB is equal to PB naught XB, and total pressure is PA plus PB, right? Then we went on to see what is your Dalton's law of partial pressures, right? So there also mole fraction is going to come, and we already mentioned that Raoult's law mole fraction, the mole fractions are in liquid phase, right? And Dalton's law mole fractions are in gaseous phase, which we already saw, right? Then we went on to do some problems. Oh, before that, we even did problems on concentration terms, molarity, mole fraction, mass percentage, all these things, right? Okay. Then we went on this wave pressure and that Raoult's law, right? And then after that, we went on to see what do you mean by an I. This is what like this was still the previous class. Previous class we started with problems, right? And then we went on to see what are ideal solutions, right? So can someone tell me what are the 4 points which you have to remember? Or, I mean, what are the four criteria for a solution to be ideal? What is it?
Raoult's law.
Yeah.
Enthalpy of mixing should be 0.
Okay.
Volume of mixing also should be 0.
Okay.
And it should have a
total adhesive.
Yeah, the cohesive force must be equal to adhesive force. Only 3 points came. What is the 4th point? Delta H mix is 0. Del V mix is 0. Adhesive forces must be equal to the cohesive forces. One more point.
Let's follow Raoult's law, sir.
Should obey Raoult's law.
Yes, absolutely. Right. You should obey Raoult's law. Okay. So that is the most important point. Okay. That should be the first point whenever you talk about ideal solution. Following Raoult's law perfectly. And then moving on to see delta H mix is 0, del V mix is 0, cohesive forces equal to the adhesive forces. We know what are cohesive forces, we know what are adhesive forces, right? Cohesive between same type of substance, solute, solvent, right? Adhesive means between solute and solvent. So all the forces of interaction must be equal before mixing and after mixing, right? That is what will make up the ideal solutions. Okay. Now, deviation from ideal behavior. There can be 2 types of deviation. What are they?
Positive and negative deviation.
Yes, positive deviation and negative deviation. And you know what are all the conditions? You have to put a greater sign for all the stuff, all the formulas you have seen. PA will be greater than P naught XA, PB will be greater than PB naught XT, so on and so forth. Again, del H mix will be greater than 0, del V mix will be greater than 0. Now you have to talk in terms of adhesive and cohesive forces, right? So now when I say positive deviation, right? Positive deviation means the vapor pressure. Yes, right? The vapor pressure which I expect, which I see is greater than what I expect, right? That means what? The interaction between solute and solvent is not that much, and that is why the liquid is able to easily go to the vapor phase. Again, I repeat, the interaction between the solute and the solvent is not so much, right? And that is why the liquid is able to easily go to the vapor phase. That means what? The adhesive force is less, the cohesive force is more, right? Okay, same way for negative deviation, you can speak all this analogy. PA will be lesser than PA naught XA, so on and so forth. You again have 4 conditions for negative deviation. And then we also saw how the graph looks, right? For ideal solution, you will see that it is going to form an exact straight line. We saw a box kind of curve in your books. I told you how where is it there, right? And you saw how is it going to change for a solution which is showing positive deviation, and for a solution which is showing negative deviation. It is going to be an upward curve for a positive deviation. It is going to be a downward curve for a negative deviation. Okay, right. Then we went on to see a special thing called as azeotropes. How do you define azeotropes?
They are liquid mixtures which cannot be separated by distillation.
Yes, absolutely. Right. So they are liquid mixtures. They are solutions. They are basically solutions, isn't it? 2 liquid mixtures means 2 liquids are added together, right? It is going to form a liquid solution or a liquid mixture, right? Now the special property of this liquid mixture is generally if liquids are miscible liquids. We know what are miscible liquids. They will form together, not like oil and water. Oil will float on water. That is an immiscible liquid solution. Solution, liquid, immiscible liquid mixture, we call it. Okay, so if it's a miscible liquid, we generally go for separation through distillation, right? Now we already told you what is the basic principle behind distillation. What is the basic principle behind distillation?
Boiling point.
Difference in boiling point. You should not say just boiling point. You should say difference in boiling point between the 2 liquids. Okay, so we took an example of ethanol and water, right? Ethanol is going to have 70 degrees Celsius. Water is going to have 100 degrees Celsius as the boiling point. So obviously, if I have a mixture, by the moment if I reach 70 degrees Celsius, the ethanol vapors will come out and that will be condensed and I'll be able to get back the ethanol liquid. And this side, you will have only water present. And that is what is distillation. Right. Now we tell that azeotrophs are liquid mixtures which cannot be separated by distillation. So we have to come up with an explanation for this. So what I told you is this liquid mixture, I have liquid A and liquid B, right? It is going to come together and it is not going to behave as if there are two liquids. This liquid mixture is going to behave as a separate liquid itself, right? So A, B are the two liquids. Now assume that I'm going to form AB. This AB is separate liquid as a liquid for itself. That means it will have its own boiling point, right? And at that particular temperature, both the liquids which are present in the mixture will come out as a gas, right? And that is the reason why we will not be able to separate azeotrophs with the help of distillation, right? Fine. Okay, now we went on to see there are two types of azeotrophs. What are they?
Max boiling azeotrophs, minimum boiling azeotrophs.
Okay, good. Right, they have maximum boiling azeotrophs and minimum boiling azeotrophs, and that is where we stopped. And I told you that minimum boiling azeotrophs will be actually found by solutions which show positive
Negative
deviation.
deviation.
No. Minimum
Positive
means
deviation.
positive deviation. Right.
Positive
you don't have-
deviation.
correct. You don't have to mug it up. I'll give you the explanation. How is it like this? Right. Anyways, so what is that? Minimum boiling azeotroph, positive deviation. What is the maximum boiling azeotroph? Negative deviation. Is that that's where we exactly stop. Okay. Fine. So first we'll try to understand what do you mean by a maximum boiling azeotroph? What do you mean by a minimum boiling azeotroph? And how is it connected to positive and negative deviation? We'll try to answer those questions now. Okay, right. Fine. Okay, so let me take an azeotrope. Say I have two liquids A and B. Okay. Say I'm just going to give you some random numbers. They might or might not be what to say practically correct. I'm just giving you some random numbers. Okay. So assume that this has a boiling point of 50 degrees Celsius. Okay, and this has a boiling point of say 60 degrees Celsius. Okay, two liquids A and B, right? And I'm going to mix them with two different boiling points of 50 degrees Celsius and 60 degrees Celsius. Okay, right. Now I'm going to mix them together now, right? So I mix them together, I form azeotrope. So something happened, right? That, see, please understand people. Say ethanol water we have, right? Not every time you will end up in an azeotrope. Okay. There should be specific ratios of these two mixed, that is ethanol and water to be mixed. Only in that particular ratio, if you mix them, they will form azeotrope. Or in some other ratio, if you're going to mix, I'll be able to separate them by distillation. Okay. Now what ratio we have to mix? It depends on so many other factors. So your temperature is a factor. So many other stuff will be there. That is way beyond our 12 classes. Okay. But for now, please understand that only in certain ratios of two liquids, only in that particular ratio, there is a possibility of forming an azeotrope. Not at all proportions and ratios. Okay, fine. So I have two liquids here which are having two different boiling points. I'm going to mix them in a proper ratio such that they're going to form azeotrophs. Okay, say I is going to form an azeotropic liquid mixture. AB is the liquid. This is an azeotrope. We'll even mention it. Okay, right. So we are trying to answer what do you mean by a minimum boiling azeotrope and a maximum boiling azeotrope. Okay, now you see the boiling points. Okay, if you see that the boiling point, there can be two cases. Obviously, it can form minimum or maximum boiling azeotrope, right? So if you see the boiling point of AB is closer to A, in the sense that say it is the boiling point of AB is say 52 degrees Celsius or 51 degrees Celsius, 51.7 degrees Celsius. In the sense, what you see is the boiling point of AB is closer to the boiling point of that of A, right? Or the other case can be, So it can even be lesser than this. There can be a case where it can be even 48 degrees Celsius. But at the end of the day, what you have to understand is if you find that the boiling point of the liquid mixture is closer to the liquid which is having lesser boiling point. In this case, you see the lesser number is 50, the greater number is 60. Okay, but anyways, so this is the first case. Second case is the boiling point of this is closer to that of D. Say assuming that it is some 58 degrees Celsius, 61 degrees Celsius, something like that, closer to 60. Okay, fine. So we understand that the smaller number is 50, bigger number is 60, right? So if the azeotrope's boiling point is closer to the smaller boiling point, then I call it minimum boiling azeotrope. Okay, but if you find that the boiling point of the azeotrope is closer to the liquid is having higher boiling point, in this case it is 60, then I call it maximum boiling azeotrope. Okay, very simple. Depending on what is the boiling point of the azeotrope, depending on whether the boiling point of azeotrope is closer to the boiling point which is lesser, or the boiling point is closer to the boiling point which is greater, I will be able to tell whether it's a minimum boiling azeotrope or a maximum boiling azeotrope. Okay, now this question is answered. Depending on what is the boiling point, I'll be able to predict whether it's going to be a minimum boiling azeotrope or maximum boiling azeotrope. Okay, fine. Right. So this we understood. Now, how are we going to connect this one to your Raoult's law, positive deviation and negative deviation is what we have to understand. Okay, right. Now, please understand, people. When I say, for example, if I take a solution which is showing positive deviation, right? If I take a solution, if I take a non-ideal solution which is showing positive deviation from Raoult's law, right? What I understand is what are the if you look at the cases, if I look at the formulas, TA will be greater than TA not XA. So what I understand is the vapor pressure I observe is greater than what I expect. That means what? Fine. Now, see, if I give some amount of heat to the liquid, what will happen eventually? The liquid will eventually go to the vapor phase. Correct? Right. Now, when I say positive deviation, already the amount of vapor is little higher because of positive deviation. How am I saying the high amount of vapors? Because there is high amount of vapor pressure. More amount of vapor, more amount of vapor pressure, isn't it? Now, can I tell that for me to how do I put it? For me to boil this particular liquid, or for me to boil this particular what to say, mixture, right? If it was an ideal solution, right, in that case, I would have actually given more temperature than in this case, what I'm seeing here. Why? Again, because of positive deviation. Like I already have greater amount of vapors present. That means the ability of the liquid to go to the vapor phase is already higher. Is it not? That's what I see here. The ability of the liquid phase to go to the vapor phase is already higher in the case of positive deviation. Right? So what I understand is that it is very, very easy for me to convert that particular liquid into the vapor phase. What do I mean by it is easy? It is easy in the sense that even if I supply lesser temperature, right? Even if I supply lesser temperature, that particular liquid is capable of going to the vapor phase. Right? That is what I understand. Right? So if I have positive, again I repeat whatever the points I told you now. If I have positive deviation, the observed vapor pressure is greater than what I expect. That means the ability of the liquid to go to the vapor phase is already very high. Right? That means what? It is very easy for me to convert that particular liquid into vapor phase. And what we mean by easy is by giving very less temperature itself, I will be able to convert that into vapor phase. That is what I understand. Right? Okay. So you see, that means what? Positive deviation liquid mixtures will have very less boiling point. That's what you need to understand. It is highly volatile. right? Same opposite for negative deviation for this thing. Negative deviation, the expected vapor pressure, so the observed vapor pressure is lesser than what I expect. That means the ability of the liquid to go to the vapor phase is not so much. It's a little difficult, right? What do you mean by it's difficult? I have to supply more energy or more temperature for that particular liquid to go to the vapor phase, right? Now you see here, minimum boiling, you can connect to positive deviation because they already have enough ability to go to the phase. And that is why we tell that minimum boiling azeotrophs are generally formed by solutions which show positive deviation from Raoult's law. I think the explanation is sufficient. Everybody understood. And same way for maximum boiling, I have to go for negative deviation from Raoult's law. Guys, everybody understood. Yeah.
So can you explain why that positive deviation vapor phase is more volatile?
Sure. So what do you mean by volatile first? Volatile means it is easily capable of going from liquid phase to vapor phase. Okay, that is what is being volatile, right? So that's what is happening here. Say before, if it was an ideal solution, say PA is equal to PA naught XA, that means vapor pressure is less. That means the ability of the liquid to go from liquid phase to vapor phase is less, right? But the moment I have positive deviation, what I understand is the vapor pressure is higher. That means what? The ability of the liquid to go to the vapor phase is higher. That means it is more volatile now. That means I have to supply only lesser temperature for it to go to the vapor phase. And that is why we say that minimum boiling azeotrophs are going to be formed by liquid solutions which show positive deviation from Raoult's law. Yes, understood?
Yes.
Okay. Mithun asked the question. Mithun, are you okay? Is it understood now?
Yes, I understood, sir.
Okay, good. Right. So we now connected minimum boiling azeotrophs, maximum boiling azeotrophs with positive deviation and negative deviation. Okay. Now next thing is, guys, right? You have to know some examples. Okay. Every time in 1 mark question you will get, right? Mention some examples for solutions which show positive deviation from the, so not positive deviation, minimum boiling azeotrophs and maximum boiling azeotrophs. Okay, now that is all given in your textbook. Okay, so if you can open your textbook, go to the azeotrope. I don't have the book with me right now, right? So what you do is you can open your books, right, and go to the azeotropes, right? There will definitely be minimum boiling azeotrophs and maximum boiling azeotropes. Look for the examples and underline them, right? I think it has maybe I can also give you some examples. Just give me a moment. Just a moment. Okay, sorry. 1 second. Okay, so solutions. I have to give you some examples. Okay, so you have examples for minimum boiling azeotropes to be, say, water and benzene. These two are two liquids which is going to form minimum boiling azeotrope. Say another example can be chloroform CHCl3 and methanol CH3OH. Again, that is an example for minimum boiling azeotropes. And maximum boiling azeotrope, say you can have here maximum boiling HCl plus H2O. You can even have, I think, HCl, H2O, H2O, HNO3. Right? So all this can be examples. There'll be many more examples in your books, right? Please underline them and know all of them. Okay, at least know 3 examples for each. 3-4 examples for each. If you can know, you are well and good. You are fit enough, in the sense you will be well prepared enough for the exams. Okay, so maximum boiling azeotrope 3 examples and minimum boiling azeotrope 3-4 examples. If you can remember, definitely you will definitely get a question. No doubt about it. Okay, so I hope all of you opened your books and marked it, right? Okay, fine. So this lets us to the first part of the chapter. The first part of the chapter is getting over with here. Okay, so the second part is going to be little more mathematical, right? Little more conceptual, in the sense, not conceptually, it is a little less, but definitely problems wise, very, very important. Okay, the next part we are going to see. Okay, so any questions from previous classes, any questions from here today, what we saw, any questions you want to ask? Okay, I suppose everything is clear, right? Okay, good enough. Okay, fine. So now in the second part of the chapter, what we are going to do is, this is exactly what we are going to do. I am going to give you a solution. Okay, I'm going to give you a solution, right? Now what you have to do with the solution is, I am not going to give you what is a solute. Maybe I'll give you what is a solvent. What is the solvent? Okay, I give you water is the solvent. I do not tell you what is the solute. I do not tell you. Right. What I'm asking is, I want to know what is the molecular mass of the solute. Do you understand the question? I have given you a solution. I know I told you what is the solvent. Solvent is water. Okay, right. Some unknown solute is there. I don't know what is the solute. Okay. Now what I'm asking you is, try to find the molecular mass of that particular solute. Right. Now, please understand, people, if you know the formula, for example, if the solute is NaCl, you know that the molecular mass is 58.5. If it is calcium carbonate, you know the molecular mass is 100. Right. But if you don't even know what is the formula, if you don't even know what is the solute, how will you find out what is the molecular mass? Right. And that's exactly what we're going to do here. Right. There are going to be certain techniques, right, we are going to use to I give you a solution and I don't know what is solute, but even though I don't know what is the solute, I will not be able to find what is there. No. But what will I be able to find is what is the molecular mass of that particular solute. So again, I repeat, even though I am not going to get the formula, even though I might not get what is there as a solute, but what I can get with what we are going to do is to determine the unknown molecular mass of that particular solute. That we'll be able to do. Even though I don't know the identity, I don't know the NaCl or KCl or some other stuff, right? But all I can do is know the molecular mass. Okay. Now, how are we going to do it? Right? We are going to do it with the help of this beautiful colligative properties. Okay, right? So first we'll take down the definition for colligative properties. Please take down. Guys, just because it's online, please do not sit idle in the sense that you will just listen to the videos and that is enough. No, it is not going to work, right? At least, especially when it comes to my class, right? It's mandatory that you sit with a notebook, because whatever comes out of my mouth, each and every word which comes out of my mouth is very, very important, right? As much as you can record, as much as is better, right? Okay. So anyways, colligative properties, will take down the definition. Right. These are the properties. These are the properties which are independent of the nature of the substance. These are the properties which are independent of the nature of the substances, but is dependent on the amount of substances present. But is dependent on the amount of substances present. Okay, I repeat the statement again. These are the properties which are independent of the nature of the substances, right? But they are dependent on the amount of substance present. Very simple definition. In the sense that these colligative properties really don't care what is the solute, whether it's NaCl or KCl or something else, but what it matters is the amount of solute or amount of substance present in the solution or in the mixture. That's what matters for these colligative properties. It really doesn't care about who are you. It just cares about how much you have. I guess if I have to put it that way, right? Who are you doesn't matter, but how much you have matters for these colligative properties. Okay, right. Now in our syllabus, we have 4 colligative properties, right? And again, as I already mentioned, why are we even studying this? Is because I have to find what is the molecular mass of an unknown solute. That is why we are studying colligative properties, right? So with the help of colligative properties, as the name tells you, as the definition tells you, you will not be able to find what is there, right? But you will be able to find how much is there. What is the amount? That will be able to. That is what is basically molecular mass, isn't it? Right? Okay. So among this, the first colligative property we are going to look into today is this: relative lowering of vapor pressure. Vp is vapor pressure. Okay. Relative lowering of vapor pressure. Okay. Guys, just give me a moment. I'll just drink some water and come. Just a moment. I'll switch off the video. I'll just come back in a minute. Okay. Yeah. So what am I telling? Yes, you are talking. The first colligative property is relative lowering of vapor pressure. Okay. We already studied about vapor pressure, right? We already studied about what is the decrease in vapor pressure also. Lowering of vapor pressure, we already discussed, right? So when I have a liquid, right? It will have some vapors now. Now these are going to exert some pressure on the surface of the liquid, and that is what is called as vapor pressure, right? By the moment I'm going to add some solute, we know what is going to happen, right? These solute particles are going to block some of the surface area, right? So by that, it is going to make it difficult for the liquid phase to go to the vapor phase. Obviously, the amount of vapors will be less, and obviously the amount of vapor pressure will also be less. So this particular part we understood, lowering of vapor pressure. And we even have a mathematical aspect of it with the help of Raoult's law. We know PA is equal to PA naught XA, PB is equal to PB naught XA. That all that we know, right? What do you mean by relative lowering? Right now, by the moment you see the term relative, right? What should come to your mind? Anybody has any idea? What do you mean by relative something?
With respect to one, sir.
Correct, right? With respect to first one thing, we have to speak, or if I have to put it very simply, right? All we're gonna speak about is the ratio, right? Relative humidity, relative vacuum, relative refractive index. All these things you see that by the moment you see relative, it is always going to be a ratio. That's what you have to understand. Okay. Now this entire term I will be able to speak about. Right. First, lowering of vapor pressure. How much is the vapor pressure lowered? Right. That means what? What is the difference between the initial vapor pressure and the final vapor pressure is what we have to know. And how can I write it? Can I write it as del P? Right. Del P only talks about the lowering of vapor pressure. Lowering of vapor pressure is delta P. That is what was finally there minus what was initially there was. Right. That is in vapor pressure. That is what is del P. Now, what do you mean by relative? Okay, I can even write del P as basically PA naught minus PA. Is it not? This was the one which was initially before mixing pure liquids vapor pressure minus PA is the vapor pressure after mixing for that particular liquid. Okay, right. Now, when I say relative vapor pressure, what you have to do is take the lowering of vapor pressure and divide it by the initial vapor pressure. As simple as that, right? So the total term relative lowering of vapor pressure is this entire term. Very simple. Lowering of vapor pressure is delta P, change in vapor pressure, right? And obviously relative lowering means you have to divide it by the pure liquid vapor pressure, that is PB naught or PB naught, depending on what you're going to speak about. Okay, right? So now I can rewrite this del P divided by PA naught. I can write it as PA naught minus PA and divided by PA naught. Right. Now let me use Raoult's law. Right. If I use Raoult's law, what can I do? I can write for PA as PA naught XA. Right. So again, I can write it like this: PA naught minus PA naught XA divided by PA naught. Okay, right? PA naught, PA again in terms of Raoult's law, I can write it as PA naught XA, right? Divided, there is a PA naught. Now, if I take PA naught common from the numerator, I will actually be able to cancel all the PAs. Right. Okay. So now I'll be able to get a statement like this: del P divided by PA naught is equal to what I have: 1 minus XA. If you're getting confused with this, take PA naught common out. So what will happen? If you take PA naught common out, 1 minus XA with what will you have? And this PA naught the numerator and the PA naught the denominator gets cancelled. So what you have is del P divided by PA naught is equal to 1 minus XA. And 1 minus XA is equal to XB. Absolutely. Right. So I can now write one more statement that del P divided by PA naught is equal to X. Right. Now, if you talk about one liquid, that should be equated to the other liquid's mole fraction. That is what is more important. Okay. So now you can even write del P divided by PB naught will be equal to XA. That will also work. Right? If you talk about the vapor pressure of one of the liquid, you have to speak about the mole fraction of the other liquid. Right? Right. Now, we started all this to determine what is the molecular mass of a particular unknown solute. Correct? Right. Now, please understand, people, this P, del P can be calculated. PA naught minus PA can be measured with the help of a barometer. You know what is a barometer? Barometer will be used for measuring the pressure, or any other instrument, right, can be used to find what is PA naught and PA. We can easily basically what I'm trying to tell you is this term can be experimentally not even calculated, measured. We can measure it. Right? Now, if you measure this term we have, right? Now you see, if you have XA or XP, right, what you're going to have, you are going to have mole fractions, right? In mole fractions, what you have? In mole fractions, what do you have? In mole fractions, you have moles, right? And in moles, what do you have? How do you calculate number of moles? Given mass by molecular mass. Is it not? Now, given mass, you know how much you're going to mix. Say 5 grams you're mixing, 10 grams you're mixing. What you don't know is the molecular mass, right? So with the help of all these calculations, with the help of all the things which you already know, right, we will be able to calculate what is the molecular mass of this unknown solute, A or B, depending on what is the solute or what is the solvent. Okay, again I repeat, this particular term can be experimentally measured, that is del P, pressure or not can be measured easily, right? Next thing what you see is this particular thing is related to the mole fractions, right? Now I know what is the formula for mole fraction. XP means NB divided by Na plus NB, right? Again in NB and Na, that is the number of mole fractions of number of moles of A and number of moles of B. We know how to calculate it. Given mass by molecular mass. Given mass is what you are going to mix. You take 5 grams, 10 grams, and you mix it. What you don't know in that entire thing, the only thing which you don't know is the molecular mass of the unknown solute, and that can be calculated. Okay, right. Now I'm going to give you one. The thing is, if at all, the moment you see anything, any problem relating to vapor pressure, right, you might have a confusion. Sir, whether I should use relative lowering of vapor pressure or can I use Raoult's law? The confusion will come definitely, right? Now, what I'm telling you, just blindly use Raoult's law. Okay, just blindly use Raoult's law. If any problem coming with this rating of pressure can also be solved with the help of Raoult's law itself, right? So what you do not use anything here for your mathematical calculation purposes. This is only for you to know, right? If at all problem comes from this area, all you have to do is use Raoult's law, and you will be able to get the same exact answer for this also. Okay, maybe we'll try an example. Okay, so we'll try to take an example and we'll try to solve both the questions with a, we'll try to solve that particular question both ways. One using this, the other using your, what is that? Raoult's law. We'll try to solve it. Okay, fine. Let me see if I have any questions with me. And guys, I'm sorry, from next class, I will show the questions, but for now, you have to take down the questions. I'm sorry. 1 second, I'm just looking for a question. Okay. Okay. Please check the question, guys. Okay, take down 5 grams of a compound. 5 grams of a compound was dissolved in 100 grams of water. Right? 5 grams of a compound was dissolved in 100 grams of water. Okay, right. The vapor pressure of the solution, you're right, VP. The VP of the solution is the VP of the solution is 4.16 kilopascal. Right, 4.16 kilopascal. The vapor pressure of the solution is 4.16 kilopascal. Right. They're telling vapor pressure of pure water. This is vapor pressure of solution, whatever I've given you now. Right. Now they're telling the vapor pressure of pure water is 4.24 kilopascal. Right, 4.24 kilopascal. This is the vapor pressure of solution. This is the vapor pressure of pure water. Okay. Now they're asking, what is the molecular mass of the compound? We are mixing a compound, 5 grams of the compound, isn't it? They're asking you, what is the molecular mass of that compound? Is what they're asking. Okay. Right. Fine. So as I told you, they're asking you what is the molecular mass. That means obviously they are trying to get you into the relative lowering of vapor pressure. Right? Fine. Now maybe first we'll try to solve it with your relative lowering of vapor pressure, and then we see what is going to happen, and then we'll try to solve it with via your Raoult's law also. Okay. Right. So I hope everybody has taken on the question. If I have to repeat the question, 5 grams of a compound was dissolved in 100 grams of water. The vapor pressure of the solution is 4.16 kilopascal, and the vapor pressure of pure water is 4.24 kilopascal. So what is the molecular mass of the compound? Is what they're asking. Okay. Fine. So let me use your what is that? Relative lowering of vapor pressure now, because we already know how to use Raoult's law. Right. First, we'll try to solve the same question with relative lowering of vapor pressure. Okay. Right. So if I write del P of water divided by P naught of water should be equal to what? Del P of water divided by P naught of water should be equal to
Mole
Mole fraction of
the
solution.
compound.
mole fraction of the compound. Very, very important. If you're going to talk about one of the components is pressure, the mole fraction should be the other ones. Right? So here it should be the mole fraction of the compound. I'll write C. Right? XC. C is the compound. Okay. Now fine. So now they have, what is del P? Del P is after and before. So after mixing it was 4.16. Before mixing it was 4.24 kilopascal. Right. So basically it should be 4.24 minus 4.16. Okay. Into 10 to the power 3 should come, because we have kilopascal. Right. That's why I'm putting a 10 power 3 here, because it's kilopascal. That's why I'm putting. Divided by what was the initial vapor pressure, that is 4.24 into 10 to the power 3. So 10 to the power 3, 10 to the power 3 gets cancelled. Okay. Now this is equal to mole fraction of the compound. Right. Now first we'll write it here itself. Mole fraction of compound will be number of moles of C divided by number of moles of C plus number of moles of water. Yes. Okay. Number of moles of C divided by number of moles of C plus number of moles of water. Very simple. Mole fraction formula. Right. Okay. Now how will you find number of moles of C? Number of moles of C given mass by molecular mass. What is the given mass in the question? Given mass of the compound is what? 5 grams. Right. So 5 divided by the molecular mass, I don't know. That's what we need to find. Right. Divided by the molecular mass, which you don't know, and that's what we need to find. Okay. So now same way, number of moles of water. What is the given mass for water?
100 grams.
100 divided by 18. This is the molecular mass of water. This we know. Right. So let me substitute it here. So you will see that it is going to be 5 by m divided by 5 by m plus 100 divided by 8. That's it. Now everything is known. The only thing which you don't know is the molecular mass, which you can calculate. Very simple. Okay. Now you have to do the calculation, obviously. Okay. So you understand that we are able to do the problem with the help of whatever the relative lowering of vapor pressure. If you find it easy, go for it. If you are finding a little difficult, sir, I'm okay with Raoult's law only, then you can go for Raoult's law also. Okay, so any questions? Very simple. I have just substituted whatever I have. Del P is change in vapor pressure before, after change in vapor pressure divided by pure vapor pressure. Now, pure vapor pressure of water, very, 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 very important, right? So we're talking about water this side. So that's why when you go for the mole fraction, that should be the other compound which you're speaking about. That is what is C. C is the compound which you're speaking. Yeah.
Sir, so in the question, if they mention solution and water, you have to treat both as equal, sir. Because in this question, the first line is given the vapor pressure of solution is 4.16 kilopascal. Then the next line is given vapor pressure of water is 4.24 kilopascal. So I got a confusion that you have to for that
exactly right.
Initial and final, I got confused between how to calculate.
Understood. Right. So what you have to understand is by the moment the first line, as you said, mentions that it is the vapor pressure of solution. That means what? It is not pure, right? Obviously, I have solute and solvent, and what I expect, we already know from all the theories that when I form a solution, the vapor pressure decreases, right? And the moment you see water I know is the universal solvent, right? So definitely that is what is going to be the solvent. And you don't have to worry about which to put first and which to put second. All you have to make sure is this del P should be positive. That's what it does, right? Obviously, why it will be positive? Obviously, I know the pure vapor pressure is greater than when I compare it with the solution where the vapor pressure would have decreased, right? Obviously, the pure vapor pressure is higher, right? So it is always, I can write it as PA naught minus PA. This is how I get it. Okay, is your question answered?
Yes, sir. Yes, sir. Understood, sir.
Okay, good. Right. Yeah, tell me, Kana.
Sir, PA naught is initial vapor pressure, sir.
Yeah, pure liquid vapor pressure.
Okay.
Yeah, fine. So that's what we wrote here. 4.24 is the pure water vapor pressure. Then 4.1 is the solution vapor pressure after mixing the water with some other solution. Right? Okay. Fine. So we understood it's pretty easy. You can go for the calculation and find out what is the unknown molecular mass. Right? Just a formula substitution. Right. Now, same thing what we'll do is we'll try to solve the same problem with help of Raoult's law. Okay. Right. I hope you have taken this down. Can I have this part? Okay, fine. Okay, right. So please understand, we are speaking about the unknown molecular mass of the solute, right? See, so I can write it like this. I write PA, or I can even speak in terms of water. However you want to speak, you can speak, right? So P of P naught, sorry, not P naught, P of water. Now, if I write P of water, what do you mean by this? A vapor pressure of mixed water. I can even write it as solution, right? Are you able to understand, people?
Yes,
Obviously,
yes.
when I say P of water, we write PA, means after mixing, right? After mixing is what we have the solution, right? So I can even write this as P of solution is equal to P naught of water or whatever the solvent it is and X naught of X of water. Right now, if you can even speak about the solution, right? But you cannot speak about that. Why? Because the solute which you're talking about is a solid, right? We cannot speak about vapor pressure of a solid jet. Okay, so now this is how you have to use, right? Whatever be the question, whatever be the solute, whatever be this thing, you have to use it only for water, right? Because only liquids will have some vapor pressure. This you have to remember whenever you're going to use Raoult's law. Okay, right. So this we understood. Okay, now P of solution is given, P of water is given, right? X of H2 you can calculate. Again, you calculate, it will be what? It will be 800 divided by 18 divided by 100 divided by 18. plus 5 divided by m. Same thing what we calculated here. This is basically what? X of H2O will be number of moles of H2O divided by number of moles of H2O plus number of moles of the compound C. Right? Now, number of moles of H2O is known. That is given mass 100, molecular mass 18, divided by molecular, again, same thing, plus the number of moles of C, which will be given mass 5, that we know. We don't know the molecule. So it's substituted here. Again, you know this, everything is known here except the M. Again, you can calculate. Okay, right? So either you can use Raoult's law or you can use relative lowering of vapor pressure for any problem, and the problems will be very, 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 very simple, except that you have to do some calculations. That's it. Okay, right? So whichever you find easy, you go for it. I find Raoult's law easy, so I go for Raoult's law. If you find plate lowering easy, please go for that. There is no restrictions. There is no, like, no marks will be reduced also. Even though they ask you the molecular mass and you're going to use Raoult's law, if you're going to get the same answer, you'll get. Maybe you'll check. You go after this class, you check it out, do the calculation, check it out. You will find that the molecular mass found in both the cases will be same. Okay, right? So I don't think you have to do much problems on this, because all the problems will be very, very similar to the Raoult's law problems. Very, very similar. It will be exactly same as the Raoult's law problems, as that we have already done in the previous classes. Okay, right? So that is about the first colligative property. What's the time? Okay, that is about the first colligative property, that is relative lowering of vapor pressure. Right. Okay, we'll move on to the second colligative property. I hope if there's any question, please ask. Is there any question, people?
No, sir.
No, sir.
Okay, I suppose everything is clear. If not, please ask me, don't hesitate. Okay, fine. The next colligative property, second one, is elevation in boiling point. BP is boiling point. Okay, elevation in boiling point. Okay, right. So first you have to understand how boiling point and vapor pressure, all these things are connected. Okay, and then only we'll be able to see. Now please understand, we are talking about elevation boiling point. So what are they trying to say is, say I have the pure liquid. Okay, I have water, for example, right? I know water is going to have a boiling point of 100 degrees Celsius. Okay, now when I'm going to add a salt, say NaCl to that, right, and I check what is the boiling point, right, you will see that the boiling point would have become, say, 101 or 102, depending on the concentration. Okay, now why this happens, right? What you have to understand, it's very simple. 100 degrees Celsius, after forming the solution, now as the name tells you, it is going to have what to say, 101 or 102 elevation and boiling point is going to happen. Now we'll see why it happens and all that we'll definitely see. Right, now we will try to understand the same stuff with the knowledge we already have from the previous concepts. Right, now you see what happens, pure liquid, pure water will have some vapor pressure. Right, now when I add a salt, obviously what I understand, the vapor pressure would have gotten decreased. We already mentioned the spaces would have gotten occupied, the liquid will face it difficult to go to the vapor phase, so lesser amount of vapors, so lesser amount of vapor pressure. We understand this, right? So this is the case where I actually go for negative deviation from Raoult's law. Is it not? The expected vapor pressure is lesser than what, but anyways, we don't have to confuse ourselves, right? So we understood why is there elevation boiling. Right? Obviously, why is the elevation boiling point? The amount of vapor pressure, the amount of vapor has decreased, the amount of vapor pressure has decreased. Now, if you want to make the liquid entirely into vapor, obviously you have to supply more energy or more temperature for it to go to the vapor. This is one explanation. Very, very legible. Any layman can understand this kind of explanation. Right. Now, what we'll try to do is we are going to first give you the definition of boiling point. We already know what is the definition of boiling point. We know that it is the temperature at which the liquid gets converted to gas. That we know. right? But we are not going to speak about that. We are going to define boiling point with respect to vapor pressure. Okay, now please take down the definition. Boiling point of a liquid definition with respect to vapor pressure. Okay, please take down. It is the temperature at which the vapor pressure of the liquid phase, it is the temperature at which the vapor pressure of the liquid phase is equal to atmospheric pressure, is equal to the atmospheric pressure. Right? So the boiling point definition goes like this, right? It is the temperature at which the vapor pressure of the liquid phase becomes equal to that of atmospheric pressure, whatever it is. Okay. Now it's pretty easy to understand, people, right? Say I have a liquid with me. Okay, right? Now it'll eventually have some vapor pressure. Right? I'm not heating it, nothing I'm doing, right? It'll eventually have some vapor pressure. Okay. Now please understand, this vapors and this liquid are able to little be in a one system, be together, is because the pressure here is high. The outside pressure is high. The atmospheric pressure we're talking, right? The outside pressure is high, and that is why these vapors are able to be in contact with the liquid phase, and that is why they're able to exert a vapor pressure. Very simple explanation. Right. Now, please understand, if I start heating it, if I start heating the liquid, what will happen? There'll be more and more amount of vapors present. There'll be more and more amount of liquid phase going to the vapor phase. Right. Now, you will see that the vapor pressure will keep on increasing. The vapor pressure will keep on increasing. Right. Now, at a particular point, you will find that the vapor pressure can no more increase. What is that point? Obviously, you can understand this vapor pressure and the atmospheric pressure becomes equal. Right? Until this point, it can accumulate. It can keep on accumulating the gaseous phase. Right? But the moment you see that the amount of vapor is sufficient enough to create a vapor pressure that is equal to the atmospheric pressure, the process stops. Right? The process stops in the sense there will not be any more increase in the pressure. There will not be any more the liquid phase going to the vapor phase, right? At the other particular temperature, and that is what is called the boiling point. So what it says is the boiling point is the temperature at which the vapor pressure of the liquid phase become equal to the atmospheric pressure, and that is what is the definition for boiling point with respect to vapor pressure. Okay, now it's very easy for us now to trying to understand why do I have an elevation boiling point after mixing, right? So obviously I know they'll now say initially without mixing there will be some amount PA naught of vapor pressure. Now when the moment I add some solid, it will become PA, which is lesser than PA naught, right? So now the whole idea is to make the vapor pressure equal to the atmospheric pressure by increasing the temperature, right? Now obviously, now in this case, when you have the mixed solution, you have to supply more and more temperature than in the previous case, because the vapor pressure is less. Here it is easy for, say, it's like this is almost like 0.8 atm, this is 0.6 atm, assume, just giving you a random number, right? This is higher, this is less, right? So obviously what I know, what is the atmospheric pressure? Atmospheric pressure is equal to 180, right? So obviously for me to make 0.8 to become 1 and for me to make 0.6 to 1, obviously 0.6 to 1 I have to supply higher temperature than from 0.8 to 1, right? And that is the exact reason why you are going to see an elevation in boiling point, increase in boiling point between the pure liquid and the solution you have formed now. Okay, so again, with the help of this difference in boiling point, with the increase in boiling point, we will be able to find what is the molecular mass of the unknown solution. Okay, is there any question, people? Everybody understood what is the definition of boiling point and how is it that I'm going to have elevation boiling point because of this? Everybody understood 2 points? Yes. Is it okay?
Yes, sir.
Okay, I suppose everybody. Guys, can you give me? Can everybody just give me a yes in the chat box or
Yes,
open
sir.
your? Okay,
Yes, sir.
1, 2,
Yes, sir.
3, 4. Only 4 people. I see. I have more than almost 11, 12 people here.
Yes, sir.
Okay, I hope everything is clear because this is a little there and there, right? Okay, so anyways, so I hope that you understood what is boiling point with respect to vapor pressure and why am I having an increase in boiling point. Okay, fine. Now we'll try to get to the mathematics. Okay, right. Okay, so now I'm going to call it delta TB. TB is the boiling point. Delta TB is the elevation in boiling point. This is what is my elevation in boiling point. Okay, now this elevation boiling point, how can I write? See, final boiling point is higher. That is, what do you mean final boiling point? After mixing, the boiling point is higher than the boiling point when I have the pure liquid, right? So I can write it as TB final minus TB initial. Final means the solution. Initial means only the pure liquid. Okay, fine. So this delta TB, right? Now there will be more and more amount of elevation boiling point. The elevation boiling point will be higher and higher and higher if more and more amount of solute is getting added. Obviously not, is it not? Right? You can easily say that the PA will be equal to PA not XA. So more and more is the amount of solute getting added, right? More and more will be the decrease in vapor pressure, and more will be the temperature which I have to supply for making the vapor pressure equal to the atmospheric pressure, right? So we can easily say that the delta TB will be equal to directly proportional to the amount of solute present, right? Now that amount which you're speaking, we are going to take it as molality, right? So we are going to say that delta TB is directly proportional to molality of the solution. Obviously, molality talks about how much amount of solute is there. We know the definition, right? That's the. Was there a problem? Guys, is everything okay? Are you able to hear?
Yes, sir.
The video got stuck, sir.
Yes, sir.
Yeah. I know something happened. I don't know what happened. Anyways, fine. So delta TB is directly proportional to the concentration of solution. How much amount of solute is there? And the concentration we are speaking is the molality term. MOLALIT. Okay, fine. I can write it like this then. Delta TB will be directly proportional to the molality small m. And to remove the proportionality sign, I can write it as delta TB is equal to Kb into m, and this Kb is some constant. Okay, now I'm going to give you some names for the Kb. Kb can be called as molal elevation constant, right? It's called molal elevation constant because it's how I'm talking about elevation boiling point, or it is called as ebullioscopic constant. EBULLIO, ebullioscopic constant, or it is also called as molal elevation constant. And this will be different for different liquids. Water will have some value, benzene will have some other value, ethanol will have some other value. So this is liquid dependent, right? Depends on the liquid. What type of liquid you use, accordingly the value will be given. And it will be given in the questions, don't worry. You don't have to remember anything. Okay, right? So delta TB is equal to Kb into m, where Kb is the molal elevation constant, or it is called as ebullioscopic constant, m is the molality of the solution, and delta Tb is the elevation point. Very simple, very simple equation. Okay, fine. Maybe we will do a problem. Yeah, we will do a problem. Okay, fine. If you've taken this down, let me give you a question. Please take that down. The boiling point of benzene, the boiling point, like BP of C6H6, right, in short form. The boiling point of benzene is 353.23. Is 353.23 Kelvin. Okay, right? The boiling point of benzene is 353.23 Kelvin. Now, when 1.8 grams of a solute, when 1.8 grams of a solute was dissolved, when 1.8 grams of a solute is dissolved in 90 grams of benzene, 90, is dissolved in 90 grams of benzene, the BP, the boiling point, the BP is 354.11 Kelvin. Right? When 1.8 grams of a solute was dissolved in 90 grams of benzene, the BP is 354.11 Kelvin.
Sir, how many grams of benzene, sir?
90 grams. Okay. Now, they're asking, calculate the molar mass of the solute. Calculate the molar mass of the solute. Calculate the molar mass of the solute if Kb for benzene. Calculate the molar mass of the solute if the Kb for benzene is 2.53. Okay, I'll come to that. Right, 2.53. Okay, first finish this. I'll repeat the question maybe. Right, the boiling point of benzene is 353.23 Kelvin. Right, when 1.8 grams of a solute was dissolved in 90 grams of benzene, the boiling point is 354.11. They're asking you, calculate the molar mass of the solute if Kb for benzene is 2.53. Okay, now what I want to know is, first we'll go to the question, don't worry. Now I want to know what is the unit for Kb. That's why I didn't tell anything. There should be something coming after 2.53. Some units would come. What can you tell me? What will be the unit for Kb? Tell me, what is the unit for Kb? From the data, from this equation, you can tell. You are
kg mole, sir.
Sorry?
Sir, kg mole, sir, because for molarity, kilogram per mole.
Okay. Okay, kg mole, that's it.
So Kelvin will be there.
Yes, tell me, what will be the overall correct Kelvin will be there?
Kg mole.
Kilogram per mole.
Kelvin, so it will be, can you repeat what you said, Kana? Right.
Kelvin kilogram per mole.
Correct. Kelvin kg per mole. Absolutely right. Right. Pretty easy, right? This is Kelvin. Delta TB, this is okay. Maybe I write here. Delta TB is equal to Kb into m. This is Kelvin. Kb will write as Kb itself. I know for molality it is mole per kg. Right. Now I have to find for Kb. So how will you write? This mole per kg comes down. So it will be Kelvin divided by mole per kg. Now you bring this to the numerator. What will happen? It will be Kelvin kg minus of kg power minus will become kg power 1, and mole power 1 is there. When you go to numerator, it will become mole power minus 1. So it is Kelvin kg per mole or k kg mole power minus 1, whatever it is. You have to remember this. Okay, so this is Kelvin kg per mole is what is the unit. Okay, fine. So I think I don't have to help you in this. It is just purely formula substitution. Can you just spend some time and try to get the answer? Right? They're asking you. They're giving you all the data possible. Right? So you just have to find what is the molecular mass downward side. Right? Go for it. So this particular question was asked in 2013 board exams. Oh, that is when I wrote my 12th boards. Okay, so all you have to do is find the modality. That's the extra thing you have to do. That's it. Not even finding it, just substitute the values, and then from that you have to find the molecular mass from the equations. That's it. So I told you molality will be very important, right? So because this is where you use molality, and the next one also, next colligative property also you'll use molality.
Sir, I got 57.14, sir.
57.14. I don't know the answer. Let me check. 1 second. Short answer, right? Yeah, 57.1 you got.
Sir, 57.14 I got, sir.
Okay, but here the almost right. 57.5 is what is given as the answer.
Okay, sir.
Okay, no issues. but you almost got the answer, right? Little maybe there and there calculation might be there, but the answer is 57.5. That's what they're given here. Okay, fine. So let us do it. Right. So first, the formula is very simple. Delta TB is equal to KB into M. Very simple formula. Now delta TB is the difference between these two, right? So it should be basically 354.11 minus 353.23. That is what is delta TB. No issues. KB is given to us. KB is 2.53 into molality. Now molality, we know what is the formula. Number of moles of solute divided by mass of solvent in grams into 1000. This is what is the formula for molality. Hope you all remember the formula. If you do not remember the formula, you cannot do the simple question. Okay, fine. So now this whatever is there, 353, approximately whatever we have, this you can calculate the subtraction, right? Now, how will I write? 253 is equal to, first the number of moles of solute. Now, number of moles I know will be given mass by molecular mass. Correct. What is the given mass? Given mass is the question is, I think, 1.8 grams. Correct. Right. So 1.8 grams divided by M, which I don't know. What is the molecular mass of solute? I don't know. That's what you have to calculate. Divided by what is the mass of solvent? Mass of solvent is 90 grams. Right. So instead of writing it like this, I can write it as M into 90. Anyway, I think you know how it works. Right? M into 90 into 1000. That's it. So all you have to find is this M. So this difference, this calculation, and you have to find the M, and the answer given in the book is, see, remember, whenever you write about molecular mass, the unit is very, 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 very important. Gram per mole, you have to mention it. Okay, you should not just, maybe, I think even if you write just grams is fine, but don't write 57.5. Right, the exact would be 57.5 gram per mole, because that is when we generally speak about molecular mass. Okay, very, very simple problems. Okay, just one formula. All you have to know is the formula for molality, and how to use it. Okay, right. Maybe we'll do some more questions in the next classes based on this only. Right. The next one, the next colligative property will be depression in freezing point. That means you're going to see that there's going to be decrease in freezing point. Exactly same formula, exact methodology. We'll see that also. Maybe we'll do problems, and next class will be, I'll just introduce you to the depression in freezing point. Okay, and then we'll do problems on both of these, because formula will be exactly similar. Delta TF will be equal to KF into M. Exactly same thing will come, right? Except that here it is boiling point, there it is freezing point, here it is elevation, there it is depression. That's it. That's the only difference. Exact same formulas, everything will be same. So I'll just introduce you to that, and then we'll go for some problems in next class. Any questions? I hope everybody understood how to do the problem. Right? Okay.
Yes.
Fine. Yeah. Fine, guys. Thank you so much. We'll meet again next week. Right? I'm just winding up the class. Thank you so much. Yeah.
Thank you, sir.
Thank you. Yeah.
Thank you, sir.